Hi, this is Dr. Collins Jones. Welcome to segment 9 of my video series on measurement, significant figures, and basic data analysis. In this segment, we will cover the concepts of accuracy, precision, error, and a few other things that are related. We'll start with some vocabulary associated with analysis and data collection in the life sciences. I always like to define assay. I get asked this a number of times when I give talks at different places. So we'll start with what an assay is. An assay detects and measures a specific molecule known as the analyte or a class of molecules. So an example would be the glucose assay. The glucose assay measures glucose. A carbohydrate assay measures sugars, which would include glucose but could also include other sugars such as ribose, sucrose, fructose, and so forth. We discussed this in the very first segment, qualitative versus quantitative measurements, and now we're just saying that we have qualitative versus quantitative assays. So a qualitative assay, again, is subjective. It depends on the observer. Generally, we are not recording any numerical values. It's sort of an estimate or an opinion. Sometimes they're semi-qualitative. We might use like pluses, 1 plus, 2 plus, 3 pluses, something like that to indicate a relative size, a relative comparison. And then quantitative assays, which is what we tend to focus on, are numerical measurements based on universal standards, right? So a quantitative assay, we have a number and a unit. These are very repeatable because they are independent of the observer. So again, quantitative assays are repeatable. We are making our measurement based on a universal standard. The measurement is independent of the observer. One of the things we also discuss is the number of replicates. And so a replicate is an independent repeat of an assay, right? So we do this 3 times. We do the whole thing 3 times. We recommend triplicates. Lots of people just do duplicates. Some places do singlets. So why do we do less than triplicates, right? Why would someone choose to do that? Well, the reason is time and money, right? Every time we do an assay, it takes time, and we have to spend money on all of the reagents that we use to complete the assay, okay? Then accuracy. Accuracy is how close your measured or experimentally determined value is to the true value or the value that is universally accepted. So accuracy, how close your value is to the true value. Precision is how close your replicates are to one another. Okay, so precision is independent of accuracy. You can be precisely inaccurate. That is, every measure you made could be very close to every other measure you made, but could still be wrong. All right. Sensitivity is the limit of detection. This is the smallest quantity that can be accurately and precisely measured. And then I just wanted to mention that, especially if we're doing assays for things like drug products, we might have to have a sampling procedure, and that is the defined method by which analytes are obtained. Okay. Then over here, just at random, I like this picture. This is not an endorsement, but I saw this picture, metabolism assay kits, and it kind of has everything you need. Metabolism assays, fluorometric assays, which is a type of spectrophotometric assay, sample extraction kits, so how do we get the sample out of a material, and inhibitor kits. And then on the bottom, they're specifically advertising the fluorometric assay kit because fluorometric assays are much more sensitive. That is, we can detect much smaller amounts using a fluorometric assay than we can a spectrophotometric or UV assay. And of course, oftentimes when we do an assay, we need to generate a standard curve, right, where we take a known standard solution, dilute it to known concentrations, and then measure a response, in this case luminescence, right, which is just flashes of light. In this case, we are measuring a response luminescence, and then we graph that, we plot it, right? And so ideally, for most standard curves, we often strive to make that standard curve a straight line, so we can use the equation y equals mx plus b, and remember, m represents the slope, and b is the y-intercept. And remember also that what we are controlling what we are changing is plotted on the x-axis. So in this case, we are changing the concentration. And each time we change the concentration, we are reading the luminescence. So what we read is plotted on the y-axis. And again, lots of times with the standard curve, we are trying to get a straight line because the slope of a straight line is constant. And you can do a regression analysis and calculate the slope, right, which is given here, and the y-intercept. So that's not within the scope of this video series, but perhaps later on I'll generate a video series on standard curves, how to generate them, how to use the data in them to calculate unknown values. All right, whenever we make measurements, their error is involved. It's unavoidable, all right? And we're going to talk in a next slide or two about different types of error, but let's just define error here, and also we're going to justify why I like to make triplicates on this slide. So there are several different ways to define error. One is error is the distance or difference between replicate measurements. That is, how close are your measurements to each other? And there may be a specification that says the measurements need to be within 0.002 units of one another, or 0.1 unit of one another, right? And the acceptable error is determined by repeating the assay literally hundreds to thousands of times to figure out, how different each measurement will be in that assay. But the other way that we'll define error, which we'll go into in more detail on the next page, error is the difference between a measurement and the actual accepted or true value that is the correct measurement. Okay, so the second definition implies that we need to know what the actual or true value is, what the real value is. In the first example, maybe we're making a set of measurements for the first time. We don't know what the true value is, but we just want to make sure that there's some kind of way to estimate the acceptable amount of error. All right. So again, the true value may be the result of a theoretical calculation. In practical or real world applications, the true or accepted value is obtained by determining the average of theoretically an infinite number of repeated identical measurements, right? So you go in the lab and you literally do thousands of the same measurement over and over again, and different workers do that same measurement over and over again, and we can compare all that data. And then finally we do this between different labs because we want this to be robust. And a robust assay is one that different people and different labs, that is labs in different locations, can get the same result, and that result is accurate. That is, it corresponds, the result that each lab gets corresponds to the universally accepted value. All right. And in some cases, the true value is obtained using a universally accepted standard, such as those as supplied by NIST. Remember, we talked about SRM, standard reference materials. So let's just look at this a little bit in terms of measurements, and not calculating the percent error, but just looking at examples of error and why I think that triplicates are the minimum number of data points you should get for any particular single assay point. So, you guys can read this and look at the measurement here, but we're going to presume that some errors have been made in the measurement in some of the examples. So in data collection set 1, maybe made by observer 1, okay, we made 3 measurements. We got 2.80, we got 2.82, and we measured 2.81 centimeters for all of these, right? So because remember, it has to be a number and a unit to be a measurement. Okay, so if we looked at the error, if we started to compare the error, we could, do the difference between the replicate measurements, and the error is pretty low. It's 0.02 and 0.01, 0.01. So these numbers are in pretty good agreement. So we would retain all of these numbers. Okay, so that's data set collection 1. Suppose another individual collects data set 2. And these are the measurements that individual 2 collected. 2.80 centimeters, 1.82 centimeters, and 2.81 centimeters. And so you can see one of these, the 1.82 centimeters, is pretty different, really by a factor of 1.0 from the other two. So we call this an outlier, and we would discard this. And in the final segment, segment 10, when we describe some basic statistics, there is a test, a statistical test known as the Q-test, that allows you to statistically be able to discard an outlier, and we will cover that in segment 10. Okay? Now, so that was triplicates. But what if you only made a duplicate measurement, and the measured values were 2.80 and 1.82? How would you know which was the correct one? And jumping ahead in segment 10, we would average this and get the standard deviation. But the standard deviation would be pretty high. This lacks precision. And the less precision we have, the less reliable the measurement is. The less precision we have, the less reliable we deem the measurement to be. Okay? All right. So, but still we took 3 measurements originally, and 2 of the 3 were close to one another, and using the Q-test, we can discard the outlier. So this data collection set is okay. We can use it. Okay? But now, individual 3. Who knows what happens when they came to work that day, but they were not focused. That individual was not focused. So measurement 1, 5.80 centimeters. Measurement 2, 0.282 centimeters. Measurement 3, 3.75 centimeters. Okay? So now these are all quite different from one another. So if you saw this, how would you know which measured value is correct, if any of them are, right? And so in this case, suppose that you didn't know the other 2 measurements. You didn't know data set 1 and data set 2. You just saw these 3 measurements, okay? You would have to say these are way too far apart to be reliable, and you would repeat all 3 measurements. If they were still very far apart from one another, right, then there's a couple of things that you would do. So first thing you do is you would just repeat this. If you repeated it and you still got this complete lack of precision, that is, the values are widely separated from one another, on the second time you repeated this, you would go to the supervisor and say something is wrong here, right? And so it could be that maybe the machine, the instrument making the measurement, isn't functioning correctly. Maybe the individual performing the measurement wasn't trained correctly, but you would go back and you would do root cause analysis, right? RCA, a root cause analysis, and try to figure out why this data set didn't give us reliable data. And then once you figured that out, you would do a CAPA, a corrective and preventative action, right? So you would write up how to do this correctly. This could involve retraining. It could involve recalibrating the instrument, maybe even buying a new instrument and validating that instrument. But you would have to do something to correct the errors from this data set 3. Okay, so let's look at the different types of errors that people can make, all right? Really, we talk about 3 main types of errors. The first one are blunders or gross error, right? These are usually not predictable. They're usually so bad that they can't be corrected. The measurement needs to be repeated. Then we have systematic errors. And in a systematic error, the same error, it occurs every time we make that specific measurement. So every measurement is the same way. Usually we can identify the source of the error and we can correct for that error. We either, recalibrate the machine, or we put in a correction factor that accounts for the error. And then a random error is not predictable. We can't control or eliminate it. It simply occurs by chance. It's a probability. So we have to deal with random errors using statistics. Okay? Now, to calculate the percent error, right? This is a way to express as a percentage how different the experimental or measured value is from the true or universally accepted value. That is, how close your measured value is to the true value expressed as a percentage. And so a lot of times when we are following an SOP or following a batch record, specifications are set for the percent error. You can't go beyond the percent error, right? If we exceed the percent error, then the measurement is considered to be invalid, or the process is considered to be invalid, and either you need to repeat the measurement or the process is stopped and you have to start over from the beginning, and you might even have to do a corrective and preventative action, a CAPA, to prevent the error from being repeated. Okay? To determine the percent error, the true value must be known. And we already said there's two ways to obtain a true value. One is we use a certified standard from someplace like NIST or ASTM, or we make many repeated measurements done by different individuals and done by different labs until we all agree on a universally accepted true value. So the equation for the percent error is equal to the true value minus the measured or experimental value divided by the true value times 100%. Okay, in some cases the percent error is expressed as an absolute value, so there's no sign, right? It's just a magnitude, it's just the size of the error, but it doesn't tell us the direction. The sign, plus or minus, tells us the direction of the error. So at least in our labs, we do not use the absolute value, because the original equation I showed you, the first one with no absolute value signs, tells us the direction of the error. Okay, the percent error could be positive, indicating the measured value is greater than the true value, or the percent error could be negative, indicating the measured value is less than the true value. So the direction, the sign, may actually provide a clue as to the source of the error. So I like to keep the sign in. Okay, so gross errors, right? Gross errors are caused by carelessness, right? You drop the beaker, you knock the beaker over, you knock the test tubes over, whatever, okay? You accidentally contaminate. Maybe you drool in your sample, who knows, okay? So whatever, but it's caused by carelessness, inexperience, not following the SOP, or making unauthorized changes to the SOP. The SOPs are there for a reason. You must follow them. So examples of gross errors: spilling all or part of a sample, improper labeling, recording the data incorrectly, using incorrect or expired reagents. Maybe you picked up 10x instead of 1x. Heating a sample too long, freezing it when it shouldn't have been frozen, using the wrong instrument to make the measurement, reading the instrument incorrectly. The instrument malfunctions during the measurement. So, maybe a circuit board burns out in the middle of the measurement, or maybe you have a power outage or some other utility fail, or maybe your statistics program didn't work correctly, or you put the wrong numbers into Excel. So, a simple example here is the instrument read 1.00 grams, but the person reading the instrument recorded 100 grams. So that's an example of a gross error. If you catch it, it should be correctable, but you're going to have to go back and redo the weighing. Okay, systematic errors are often caused by improperly calibrated equipment. Could be caused by environmental issues. And so I've shown a balance here. Balances can be subject to temperature changes, especially electronic balances, right? So you need to keep those at the temperature you're going to use them at for multiple hours before you use it. You need to keep the balance away from air currents. That means overhead heating ducts. That means opening and closing doors. Okay. Systematic errors could be caused by poor experimental design, or they could be caused by observer bias. You're not really looking at things correctly. So examples of systematic errors: incorrect zeroing or calibration of the balance of the pH meter, of the pipettement, of the spectrophotometer. So all of those, you've either zeroed it incorrectly or you've calibrated it incorrectly. If you're using a spectrophotometer or something like that, you have the wrong blank, all right? So you record a positive value even though the readout was negative, all right? So and you go, who would do that? Well, I hate to say it, but I've had some students who thought the number should be positive. The instrument displayed a negative number, so they just ignored the negative value and recorded it. So it's important that you maintain data integrity at all times. You always record what you see, okay? Systematic errors often can be eliminated or corrected for once the cause is known. So maybe you knew that every measurement is decreased by 2.149 whatever units, absorbance units, pH units, grams, due to a calibration error. Then once you discover that, 2.149 becomes the correction factor and is added to every measurement. Okay, so systematic errors should be correctable, and it might even be that they can be eliminated. So again, if you have a systematic error, they're giving you precise readings. They're just inaccurate readings. Okay, random errors, again, can be caused by environmental changes. They can be caused by inconsistent technique. You don't use the micropipette smoothly. You don't weigh things always correctly. And they can be caused by instrument noise. So all measurements have some kind of random error. And again, examples of random errors: small variations in the balance due to air currents. So what you see in the panel on the right is I actually sat in my lab and I put on a beaker. You can sort of see the beaker sitting on the weighing pan. And we have this weighing pan enclosed with a glass circle and a lid on top to minimize the effect of air currents, okay? But I sat there and watched the balance, and I took pictures of it. And you can see that the uncertain digit is actually uncertain. I sat there for about 2 minutes, and every time the uncertain digit, the last digit, fluctuated, I took a picture of it, okay? And so this is really more than air currents. This would be due to electronic noise. And you guys can see some of the other errors that I put in here. We can have errors due to inconsistent tip diameters. You get what you pay for micropipette tips and serological pipettes. If you don't read the graduated cylinder correctly, remember parallax error, right? Even sometimes leaning on the bench with the balances can affect the weight, all right? And then there's electronic noise. So again, we reduce the effect of random errors by making repeated measurements, triplicates, ideally, at least in my lab, and by using statistical analysis. Okay, so random errors, there isn't precision here. They're kind of spread out because they are indeed random. They're just a probability. Okay, so let's look at noise, because everybody talks about noise, and you know, the circuit design people and the control circuit people are going to roll their eyes at this explanation, but it works, and it kind of helps you conceive of what's going on inside any electronic measuring device: an electronic balance, a spectrophotometer, a pH meter. Okay, so noise in electronic measuring devices refers to unwanted signals which may cause error in the measured value. It can be electronic noise in all instruments. It could be photon noise in spectrophotometers. And there's lots of information available about this on the internet. I've just sort of condensed this into one slide, if you will. So some noise sources are systemic and some are random. Systemic noise can be corrected for by a blank and a standard curve. Random noise is averaged out using statistics. Electronic noise can be reduced by having a stable power source. So often what this means is you have a filter or some type of capacitor where the line voltage coming in from outside is stored up and then is discharged at a constant rate, so there's no fluctuations in the voltage. So I don't know if you guys know this or not, but at certain times of the day, usually in the morning and the early evening, when people are either getting ready to go to work or coming home from work and turning everything on, coffee pots, TVs, ovens, stoves, there are fluctuations in the line voltage. Normally you don't notice this, but super sensitive instruments may be affected by changes in the load across the power lines, all right? So the ways that we minimize this is we make sure the room temperature is stable, we make sure the instrument is warmed up, we use the electronic filters, and you can actually have firmware in the instrument that does some statistical smoothing of the noise, all right? So sources of noise: thermal noise, changes in voltage or current due to temperature changes, and shot noise. I could spend a lot of time on this, but it's just due to the quantized, the random nature of electrons as they move. And there's all kinds of equations to describe all this stuff, but basically, here's kind of what we look at. We have some electronic noise. The signal is bouncing up and down, okay? All right, and so I'm just randomly said the noise signal output is 0.032, and this could be volts. When we put the analyte in to be measured, it also gives a signal, all right? And so I arbitrarily said, let's call the signal 0.250 maybe volts, okay? So what you really see, right, in the readout is the electronic noise plus the signal output from the analyte. Okay, so the whole output that you see is going to be 0.282, but happily, right, most of that signal is due to the analyte. Most of that signal is due to the analyte. And so generally what we say, when the signal of the analyte to noise ratio is greater than 3, the measurement is reliable. So that's why, for example, in our labs, we say that if you're using a spectrophotometer, the minimum reliable absorbance reading is 0.100, and then for other reasons, we can't go much above 1.2 because we saturate the detection system and it can't detect reliably any absorbance values greater than 1.2. All right. So this is a reliable signal. We have enough analyte in there to give us enough signal that the signal to noise ratio is greater than 3. But if we don't have a lot of analyte, here we still have our electronic noise, but maybe the analyte signal isn't quite as strong. Maybe it's too dilute. It's not concentrated enough. So now when we look at our signal output, it's only 0.046. Okay? So when we combine the two, look, there's not really much difference between the noise signal and the analyte signal. And so the observed signal is 0.078, okay? And our signal to noise ratio is less than 3, and the measurement is not reliable. So that's what we mean when we talk about noise. And again, noise is random, all right? The noise is random, and so we just need to make sure that we get enough of a signal from what we're trying to measure that it's at least 3 times higher. That signal from the analyte is 3 times higher than the noise signal. All right, now, examples of calculating percent error. This is really easy. This is what we call just a plug and chug. So the average experimental value was determined to be 35.23 grams, and the true value is 28.50 grams. So our equation to calculate the percent error is true value minus measured value over true value times 100%. Right? So there's our true value, 28.5 grams, and our measured value is 35.23 grams. So we just plug those numbers in place of the words, right? True value 28.5 minus 35.23 divided by 28.5. So this is a negative 23.61%. That's a pretty high percent error, right? I'm not sure I'd want to buy something or use something like that to test me if it gives me almost a 24% error. Okay, example 2. The measured value, and did we pay attention to significant figures in this? Yes, we did. 4 significant figures. The measured value was determined to be 0.00997 moles. The accepted value is 0.01000 moles. Determine the percent error. Same thing, plug and chug. Write the equation down, identify the accepted value or the true value, which is 0.01000, right? And the measured value, which is 0.00997. Plug those numbers into the equation, solve it, and we get 0.300%. That's not bad for a percent error. So we're happy with that. And it's positive. Okay. The laboratory determined value was 3,286.7 milliseconds. The known value, which would be the accepted value, is 3,500 milliseconds. Determine the percent error. So again, it's just a plug and chug. Okay. Known value is the true or accepted value. Experimental value is the laboratory value. Plug the numbers in, and we get 6.0943%. And again, did we adhere to the proper number of significant figures? 5 here, 5 here, 5 here. So we're good. Okay. All right. Now, when we talk about testing, people always talk about things like false positives and false negatives, right? So if the measured value or the experimental value or the test value is the same as the true value, okay, then this is correct. There's no error. So experimental value is true, actual value is true, all right? If The experimental value tells us that the analyte is present. So maybe this is the COVID virus, all right? Maybe it says glucose is present, but it's really not present, all right? So it tells us it's present when it's not. This is a false positive. We say it's saying it's positive, but it's not really positive, and this is called a type 1 error, okay? If the measured value or the experimental value says the analyte is not present, you don't have, you do the COVID test, it says you don't have COVID, but you really do have COVID, it just made a mistake, right? Or it says there's no glucose present, but you have glucose present, okay? Then this is a false negative, all right? It says it's not there when it really is there. That's a false negative, and that is called a type 2 error. And then when our experimental value says it's not there and the true value of the standard says it's not there, then this is also correct and there's no error. Okay? All right. How do we minimize measurement error? We've kind of discussed this throughout, but let's just talk about this. One is we pay attention to instrumentation. We use the correct instrument. We make sure the instrument is calibrated and maintained. People are trained how to properly use it. Right, and we maintain current technology, right? We can have documentation and design, so we use SOPs, right? So we have specified procedures about how to use that particular piece of equipment. We have controls. We have positive controls, things that tell us if the equipment is working correctly. That is, we actually we know it's supposed to give us a positive result, and it does give us a positive result. We have a negative control. So a negative control says we don't see a signal, right? So if we put the negative control in and we actually see a signal, we know something is wrong. If we put the positive control in and we don't see a signal, we know something is wrong. If we put the positive control in and we do see a signal, this is good, right? And then sometimes, especially when you're at companies that do a lot of testing, they randomly insert known controls that the operator, the person actually doing the testing, doesn't know about, just to see if they get the right result. All right. And then, of course, personnel, we need to train people properly. We need to evaluate the success of their training. And occasionally we need to do retraining. And then for random errors, we use statistics, and we need to make sure that we choose the proper statistical tools. So once again, just to summarize this, accuracy, how close your measured value is to the true or standard value. Sorry for that typo there. And we want a low percent error. Precision is how close your replicates are to one another. So we have a small standard deviation. Sensitivity is the smallest amount that you can reliably detect and measure. So ideally, the signal to noise ratio is greater than 3. The limit of detection, this is the minimum and maximum amount of analyte that can be measured reliably. So minimum amount is the signal to noise ratio. Maximum amount is the saturation of the detector. So if we exceed the ability of the detector to detect changes in concentration or analyte, then we need to do a dilution. Okay? And so we usually, within a particular assay, we specify the range, the concentration range, that can be reliably measured. And if we don't know what the concentration of our analyte is, then we do serial dilutions to determine what the correct dilution is to bring it into the range that it can be reliably detected by our measuring instrument. Okay, so let's just give some numbers here to look at the idea of accuracy, precision, and outliers. And then in the next and final segment, we're going to go over basic descriptive statistics, okay? So we're going to assume the true value is 12.12 milligrams per mil, okay? So in the first column here, our measurements are accurate and precise, right? They're close to 12.12, and they're close to one another. And so, lots of people who explain this like to use the bullseye idea. So all three of these are pretty close to the bullseye on a target. Okay. Next, these are not accurate, but they are precise, right? The correct value, again, is 12.12 milligrams per mil, but these are all roughly 7 above the true value. So this tells me that this is a systematic error, right? They're all off by the same, so it's probably a systematic error, but they are precise, they're just not accurate. So we should be able to correct for this. Accurate but not precise, okay? So here the values, the measurements, are really different from one another, but if you were to add them together, it turns out that the average would be around 12, okay? So if you were to average these out, right, the average would be around 12, but we would have a very high standard deviation, so this lacks precision, okay? So in this case, this is probably operator error. The person doing the assay is probably making a mistake, so we'd need to do some retraining. That much randomness is usually not due to instrument error. It's usually due to operator error. Okay, and then here, not precise, not accurate. Again, this could be operator error, but this could also be instrument error. This is just bad. Okay, so this is not good. And the readings are all over the place. And then finally, we want to bring up the concept of outlier again. An outlier is a measured value that is very different from the other repeated measured values. So an outlier is a measured value that is very different from the other replicates, from the other measured values of the replicates. And so here's our outlier, okay? And you can see it lies far outside the range of the other measurements. And so in general, we discard outliers, but as you'll see in the next segment, we use the Q-test to statistically prove that we can discard an outlier. And that is the end of segment 9.